Okay, so we've done a majority of the derivative rules for Calculus 1, and what I want to do now is discuss higher order derivatives, um, which is just it's pretty important, especially in physics or anything relating to rates of change, right? So in derivatives, right, we denote it typically in two general ways, d over dx and f prime of x. This would be f of x. This is generally how it is depicted. Uh, the second derivative of this would be d squared over dx squared of f of x. The second derivative of this would be f double prime of x. Okay, so this can kind of be interpreted like you're taking the derivative of the derivative. That's essentially what you're doing here. So d over dx, and then you have f of x. You're taking the derivative of the derivative here. So in other words, if you want to think about it like this, I don't know if it's proper to, but you could like multiply in here. You're distributing it, right? D squared over dx squared of f of x, right? And you'll notice it's not dx squared like it is dx squared here with parentheses. And from what I've learned online, the main reason for that, or what they think the reason was, is just because that's just over time. It was written in different ways, and I guess I think the justification was like mathematicians want to be quick and fast, and they just want to write it easy, and they're lazy or something like that. That's the justification I heard from I forget his name, but yeah. So don't pay too much attention to that. Just kind of think of this as an operator, not really as something to be messed with, because when you actually look at it, it can be a little bit iffy when you're trying to do operations with it. Okay, so anyways, the second derivative is the derivative of the derivative. Okay, so let's talk about um, this function s of t. Now s of t, S stands for position, not speed. That's just how it's denoted in physics. T is t. It's time. T is time. So that one makes more sense. So it is a graph of position with respect to time. Okay. So if I were to make just kind of like, I don't know, a rather large graph here. Let's say I have some line like this. The x-axis is t, the y-axis is s. And let's say that s is in meters, and we have seconds as our x-axis. So what we're figuring out here is how many meters have we traveled in t seconds? Or in other words, how much has our position changed in t seconds? Okay. So if you think about it like that, if we say, let's split this up into a couple pieces here. Okay. So let's say that each of these is like 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds. Okay. And let's label the y-axis to be 1 meter, 2 meters, 3 meters, 4 meters. Oh, well. Okay. So we have this graph here. All right. So the way you interpret this graph is going to be at 1 second, we have, well, we're a little less than 1 meter. Once after 1 second, we've traveled a little bit less than 1 meter. After 2 seconds, it looks like we've traveled just about 2 meters. After 3 seconds, it looks like we've traveled a little bit over 3 meters. After 4 seconds, it looks like we've traveled a little bit under 3 meters. And after seconds, it looks like we're somewhere between 2 and 3, like 2.5 maybe. Okay, so that's how you're interpreting this graph. Now, if I want to take the derivative of this graph, what I'd be getting is the rate of change. So, in other words, how quickly our position is changing with respect to time, right? And this is denoted, and I'll explain it in a moment. This is denoted as, well, there's a couple ways to note it. One of the ways is going to be VAG. This is your average velocity. V sub AG, AG means average. And this is going to be equal to displacement over time. Or, well, I mean, travel time. I need to be specific there. And this is the same as saying, for example, the change in S over the change in T. And this is the same as saying, let's say we have 2 points, f of t plus delta t minus f of t over delta t. So what we have here is s sub 2 and s sub 1, and we're subtracting them to give us the difference between those points, the displacement between those 2 points. Okay, so that's our displacement between points. Okay, that's what displacement means. Displacement, for example, one way to think of it is, say you're at 5, or well, let's start at 0. Say you're at 0. Say you travel 5 units, and then you travel back 3 units. So we travel over here 5, and we travel back 3. Our displacement will be 5 minus 3 is 2. Our displacement doesn't care how far we've traveled in general. It cares how far have we traveled relative to where we started. So if we started at 0 here, if we started at 0 and we ended up 2 units away from 0, then our displacement is 2. Our displacement wouldn't be 8. Even though we've traveled 8, we've traveled 5 here and 3 back, we've traveled 8 units, but our displacement cares about how far are we, what is our distance, what is our distance from where we started. Okay, that's displacement. Okay, so in this instance, we have S2 minus S1. So we have some position 2. We can say our position 2 is like right here. And our position 1, we can say is right here. Okay, so we are subtracting these positions. And we're saying this change in t is like our little extra nudge on the x-axis to get us to a new position. However that nudge is. Notice there's no limit here saying that that's approaching 0 yet. Okay, so then think about it. This velocity here, the average velocity. So you'll notice change in s over change in t is the same as change in y over change in x. We're just using different functions here. This is just equal to slope. And the reason it's not a derivative is because derivatives are slopes of like the tangent. This is just the derivative between 2 points, or not the, I'm sorry, the slope between 2 points, S2 and S1. And we have over here, the bottom is only this one variable because we're saying we have the change, or what we have is t plus the change in t minus t, right? This is our x, this is our x2, and this is our x. So when this is works in derivatives too. That's why it's just change in x. That's why there's only that one variable there, because this and this cancel. So that's just how that works. That's just the baseline of it. But yeah, okay. So this gives us a slope, and a slope is your average velocity because we're concerned with these 2 points here. So the slope between these 2 points is your average velocity between those 2 points. Okay, as displacement, however, here, let me move over here. If we want the instant velocity, that would be our derivative. And that is just denoted as v of t here. And this is equal to ds over dt, right? And that's the derivative notation. And this is the same as the limit as delta t approaches 0 of this same thing over here. So this is kind of where derivatives come from in general. This is like that's a t. This is kind of where derivatives come from in general. They're really not too complicated of an idea. Like it's something you can grasp it intuitively. So don't be like worried. Just remember to keep an idea of like what they are intuitively in the back of your head when you work when you work with them. Okay. So the reason that this is your instant velocity, which is what this is called, it's velocity instantaneously, or your instantaneous velocity, is because that's what a derivative is. It's your instantaneous rate of change. Velocity is a rate of change. Now, when they say rate of change, you can't have a rate of change in an instant, in a moment, right? Because change implies that you're comparing two things, right? A rate of change implies that you're comparing the rate between two different things. So in this case, it would have to be two different points in time. When they say instantaneous, they mean extremely close, like infinitesimally close. Like there's practically no distance, but obviously there's a little tiny bit of leeway. Because as you see here, if the derivative, if delta t did approach 0, if it became 0, it would be undefined. So you can't do that. Anyways, just to clear that up, when they say anytime you hear instantaneous rate of change, just know that's kind of an oxymoron. But anyways, moving forward, a quick side note, speed is equal to the absolute value of v. Velocity has magnitude and direction. Speed only has magnitude, right? We don't say we're going negative 20 miles an hour. We say we're going 20 miles an hour, and then you might add backwards. But speed itself is just how fast you're going. It doesn't matter. It doesn't care about which direction you're going. Velocity cares which direction. So that could be up or down. That could be left or right. That could be back or forward or whatever. Well, I should probably keep that. Okay. So just know the derivative, in other words, I could rewrite this as you see here, ds over dt. That's this right here. We're taking the derivative of this function. That is velocity. That is your instant velocity, or your derivative. And in other words, velocity is your rate of change. In this example, this is slope, so ignore that. But in this example with position and time, you're saying, okay, what is the rate at which our position changes in respect to our time as our time approaches, as like our, how can I say this, as our other time that we're comparing it to approaches 0, or approaches the same value. dt is like an incredibly small value. Change in t could be anything. Change in t just refers to change in t. But specifically ds over dt means like you're saying basically this is instantaneous. Okay, so just know, if I want to, I could say s double prime is equal to v. I could say ds over dt, or no, I'm sorry, s double prime is not v. S prime is v. I could say ds over dt is v. That's what that is, okay? If I want to take the double prime of that, you may be wondering, okay, what's the double prime in relation to s of t? Double prime, in this case denoted as s double prime, or you could say d, well, that's the wrong one, d squared. You can also say d squared s over dx squared. I typically just say d squared over dx squared s, because if you think about it, this s, if you were to multiply in, it'd just be right here. So, I mean, that's how I think of it. Anyways, though. Okay. So if I want to figure this out, this is equal to acceleration. The derivative of velocity, right? Remember, this is the derivative of a derivative. So the derivative of s was velocity. So the derivative of that, which is our second derivative, is equal to acceleration. Our derivative of our position with respect to time is the rate in which our position changes with respect to time. And the derivative of that is the rate at which our speed changes with respect to time. Our velocity changes with respect to time, and that's acceleration. So how quickly we accelerate, how slowly we accelerate. Acceleration has magnitude and direction as well. So if I were to say, well, if I were to have a graph here, I'll just make a graph. And let's say that we had some graph like, let's say S of t was like, just like a parabola, for example. And let's say it's x squared, or well, t squared. It's equals s, okay? So if that's what that graph is, the derivative of that, keep that. The derivative of this is going to be 2t would be velocity. The derivative of 2t is just going to be 2. So our acceleration in this case is constant. So let me just write the graph of that derivative. That's going to look like this. It'll be 2t. That's that line. And the derivative of that is just going to be our slope right here of a linear function is just going to be 2. And wherever that is just going to be this flat line at y equals 2, or at s equals 2. Or not s, at a equals 2. Okay, so that's just a way to think about all these. And if you want to go further to your third derivative, you'd have jerk. And jerk is like, it's the change in acceleration. So that'd be like anything. It's kind of it's hard to explain given what I've already said, but it's like changes in your acceleration, right? So like say you're jerking this way or jerking that way. That's what that tells you. And a way to interpret these graphs, if I said that our velocity, if this is the graph of our velocity, and let's say it's like, I really should have multiple quadrants here. Let's say it looks like this. And let's say that it's like just y equals x here. If this is the graph of v, of just v, this right here, when it crosses the x-axis, that means that our velocity is 0 because our y-axis is v and this x-axis is t. So at t equals 0, our velocity equals 0. And you'll also notice if t is, well, in this case, these are all negative rates of change. Okay, so that means that the velocity is going in a negative direction. And a way to think about this is you'll see it's going up. So it's going in a negative direction, but it's slowing down because you can see it's getting closer and closer to being positive. And a way to think of that is like, say you're dropping a ball. That ball is going down, but then it falls in like water or something, right? Then that ball is going to fall down, but it's going to fall slower. And then say it falls in like honey or something, which is a lot more dense. I don't know if that's the right word. Then it's going to fall even slower. And then eventually it's just going to stop and start going up. That's what this graph says. It's just going to stop at v equals 0, and then it's going to start going up. Its speed is going to start increasing rather than, or well, okay, its speed was decreasing, and then it increased. So I don't know if that makes any sense. We're decreasing here, and then we're increasing after we pass v equals 0. Okay, and then your velocity would just be, like I said, like a flat line here, depending on what that slope of this line is. In this case, it's just going to be 1. So we're going to have our acceleration be 1. And you can see that here. It's a constant slope, right? It's a constant rate of change along this whole velocity. So our acceleration is going to be constant. We're going to be slowing down or speeding up at a constant rate. Okay. So that's a couple ways to kind of interpret higher derivatives, or in kind of context of velocity, speed, acceleration. There's more to learn here, but I think it's really interesting how you can incorporate this into velocity. But yeah, and that's going to be it for um, higher power derivatives.